Okay, so let's talk about linear discriminant analysis in today's session. So, what is the difference? As time goes on, you'll understand how linear discriminant analysis is different from principal component analysis. Okay, so linear discriminant analysis is also a dimensionality reduction technique. So, this also will be used to reduce the dimensions in the data. Okay, often used in supervised learning. So let's keep that supervised learning term aside for some time. So what this linear discriminant analysis basically will tries to do is it tries to do the classification problems. So this is basically used to classify the categories in the data. Okay, we will also come to know what is categories means, but just try to see the terminologies that we will gradually understand. It aims to project the data onto lower dimension spaces while maintaining the ability to effectively separate classes. Okay. What does PCA will do? PCA will just do dimensionality reduction. It transforms the data in higher dimensions to lower dimensions. Okay, that's we have seen. It just covers the variance in the data. It finds a direction which covers the most variance in the data, right? So that is what PCA will do. But what LDA will do is, along with that lower dimensionality reduction, it has also the capability to effectively separate the classes. Okay. When you say effectively separate the classes, there are two classes here. Okay. The first class is viral and the second class is bacterial. Okay. So these are, we have different patients and we have done tests on them, different tests. One is the CRP test and also the other one is temperature test. And these are the values that we have got. Based on these values, we found out that the patients who has these values are have viral infection, and the patients who has these values are have bacterial infection. Okay, now, so basically let's suppose um, let's suppose these are the tests that have conducted on different patients, and it took around like 7 days or 8 days to get these test results. And based on these results, we got to know the infection of the patient. Okay, so only the antibiotics will work on bacterial patients. They cannot be given to the viral the patients with viral infection. So if a new patient comes, now we have to find out, we cannot, I mean, it's ideal that we do the tests on them, wait for 7 days to get the test results, and then treat him with antibiotics, or not treat that patient with the antibiotics, right? So instead of waiting 7 days to treat him, if you're able to figure out based on the earlier values that we do have, if we can figure out whether he has the bacterial infection or not, would be easier, right? It just takes very few hours, or a very few minimal tests to analyze whether he has bacterial infection or not. So what we are all trying to do here is, we want to classify the data, and whenever a future patient comes with different values, we also want to classify to which category he belongs to, right? That is what classification basically means. Classification means group together all the similar categories. Okay, so that is what classification means. So what LDA basically will do is, LDA not only will do dimensionality reduction, but it also has the ability to effectively separate the classes. So here there are two classes or categories. The first category is viral and the second category is bacterial infection. Okay. Right. So now I have drawn some diagrams here. Okay. So I took the graph along, I took the graph on y-axis, I have taken CRP values, and I plotted different values on this particular graph. Okay. These are the patients, these are the values of CRPs for the patients with viral infection. And these are the data points for the patients with bacterial infection. Similarly, I have drawn temperatures with um, temperatures of different patients, and this is how they look like. Okay, so these are the data points of different patients. Now, our main target is to classify this. So we should be able to classify um, or group the patients with virus infection and group the patients with bacterial infection. So if you just draw a line somewhere in between, is that like, let's suppose if you take the mean of all these values and draw a line over there, are we able to effectively differentiate the different groups? So, like if you take this particular group on the above, it shows that, you know, they all, I mean, we have mixed patients in this category, right? So even if a new patient comes over, we cannot say whether he belongs to bacteria or virus. So we have these mixed groups. When we take this temperature um, as the only parameter to analyze the patient has virus or bacteria, we were not able to separate the data, right? But even if you take that particular mean value for these CRP values as well, somewhere like this, it also do have like mixed patients in each category. So with just CRP values and temperature, we were not able to actually separate both the classes effectively. We have, even if you take the line anywhere, right? So with just CRP values, if you take any value, we are not able to effectively separate both the classes, right? So the main goal that LDA tries to achieve is to separate both the classes effectively. And how it will do is something that we are going to learn just now. Okay, so that's just an introduction for linear discriminant analysis. So linear discriminant analysis is used to do the dimensionality deduction, and also it has the capability to effectively separate the classes. Okay, and now we have plot the values for both the classes, and we found out that when we take the individual dimensions, we are not able to effectively separate the classes. Then now we are going to understand how LDA will actually achieve that separation of these two classes. Okay, so if I go back to the next slide, now I have taken temperature along x-axis and CRP values along y-axis. Okay. So now these are the graphs I have plotted. This is the graph how it is looking like. So these are the points which belongs to bacterial patients, and these are the points uh, we have got for the patients with viral infection. And now if you look at this particular line, it is able to effectively separate both the categories or both the classes effectively. So if now you now your main goal is to find out this particular line, right, which is separating both the classes. Now how we do the dimensionality deduction and how we actually separate the classes is something that you're going to see now. So what LDA will basically try to do here is that it's going to find out this line which actually do the dimensionality reduction and also separates the classes effectively. So look at that. So now we plotted both CRP values and temperature values. And now we also able to figure out a line which is actively, separating both the, uh, you know, uh, both the classes. Now we got two dimensionality. I mean, these are called as discriminate scores. D1 and D2 are called as discrimination scores. So now what we are trying to do here is we are trying to find out the discrimination scores along different axes. Now, if you look at D1, it is able to right separate both the classes. The look at the line D1, it is effectively separating both the classes. Now if we just do that projection, okay, onto the D1 axis, you are able to reduce the dimension and also separate the classes effectively. Now look at D2 line. I mean, this is the D1 line that you're seeing right now. And now what actually happens is if you look at line D2, the dimensionality score D2, I mean, we have two dimensions. So we tried to find out two parallel dimensions, like how in PCA, we were able to find out two principal components for the original dimension. So the number of principal components will be equal to the number of original dimensions. But how we are reducing the dimensionality, we are just trying to put a critical value for the amount of variance that we want to capture in the data. Based on that variance value, we are choosing the number of principal components that we want to go with. So those principal components will be the new dimensions. Onto those new dimensions, we are transforming the points from the original dimension to these new dimensions. How do we transform? What is the formula for, how do we transform a point from one dimension to the other dimension? Or what is the formula to project a point onto a particular vector? How do we do that? Projecting a point x onto vector u, how to actually find out that particular point on this vector u? What is the formula for that?
X dot u by u dot u bar.
Right. So that is how you calculate the projection of a point onto a particular vector, right? So that's how you project the points from the three dimension to the new two principal component dimensions, right? We are just doing a matrix multiplication. So you will also see today how the matrix is transforming the data from one dimensional to one dimensionality to the other dimensionality. I'll actually show that intuitively. As I haven't showed in the last session. I think I already explained how that matrix will do transformation, but I'll also take up more examples today to explain you that. But leaving that concept, that similar way, it also tries to find out new two dimensions or dimensionality scores of different classes. Okay, so this is D1 and this is D2. D2 is not able to separate both the classes effectively. Look at this on the top portion. You are seeing, the mix of both the classes. In the lower part of D2 also, you are seeing the mix of both the classes. So D2 is not effectively separating the classes, right? So, but D1 is able to do that. So what we're going to do is, as we know, D2 is not able to separate the classes effectively, we just go with D1. Okay. So now what we have done, we have reduced the dimensionality from two dimensions to one dimension, and we are also able to separate the classes effectively. Now we have to get rid of D2 because D2 is no more valid for us because it is not able to separate the classes. Right? So those dimensionality scores on D2 were not able to actually effectively separate the, both the classes. Now just project those points onto D1. So once you project those points onto D1, we were able to successfully separate both the classes or accumulate or classify both the classes into different categories. Just look at this part. Now, if you look at this particular data, we were able to successfully separate both the points, right? So this is how we are doing accumulation of both the classes. So all these points belongs to viral infection, and these all points belongs to bacterial infection patients. Okay, so that is the main goal of linear discriminant analysis. Okay, so how linear discriminant analysis will achieve this? We will also go to put out some objectives for this LDA, like how we have done for PCA. For PCA, the objectives are to maximize the variance and minimize sum of square distance, so that we come up with the direction of maximum variance in the data, which is nothing but the eigenvector of covariance matrix. And we also derived how eigenvectors of covariance matrix gives the most variance in the data, or that we have already shown you with the derivation as well. So we constructed an objective function and we have applied you know derivative and equating that to zero. That is how you find out the maximum value or minimum value of something, right? That's how we derived, and we came to know that the eigenvectors of covariance matrix are the principal components. That's how we derived. Similarly, for LDA also, we are going to do the same thing. But now we are just trying to understand intuitively what LDA is trying to achieve with the data that is given. Okay. So the major difference between LDA and PCA is, for PCA, this particular dimension is not a concern. We don't feed this dimension to PCA. For PCA, we will not feed this. We just feed these two values for PCA because it just focuses on finding the maximum variance in the data. It never bothers about classifying the categories in the data, or it don't have this that capability to effectively separate the classes. So there is no need to actually feed this dimension of whether that belongs to viral or bacterial. We don't feed this dimension to the PCA, but for LDA, actually has to feed this data as well, because it is going to understand which point belongs to which class only if you feed this particular data. That's the one of the differences between LDA and PCA. So LDA is also a linear combination of, you know, um, LDA is also a linear combination of the dimensions in the data. Okay, look at this. How do linear discriminant analysis will differentiate the data? It calculates the discriminant scores and plot the data points using those discriminant scores, so that we will get this kind of dimension. So if we calculate the discriminant scores for all these points, these are the values that we got for different points in the data. Okay, so if you calculate the discriminant scores for this, it falls here. If you calculate the discriminant scores for this, it falls here. Somewhere every point falls. The discriminant scores of every point will looks like this, and for the bacteria they look like this. Okay, so when we plot that, we were able to actually differentiate the data. Okay, so now the main goal is to find out this particular equation that is actually able to, that has the capability to separate the classes, and also were able to find out a new dimension, which is the linear combination of the original dimensions. Okay, so if I go back to the next slide, so look at this. So we calculated the discriminant scores of, different dimensionalities that are available over here. Okay, so right now, look at this. We calculated the scores using this formula. Let's suppose based on all the calculations that we do, if we got alpha 1 as 0.11 and alpha 2 as 0.70, we got this particular linear discriminant analysis equation. So based using this equation, which is the discriminant scores, we calculated the discriminant scores for different data points in the data. And if you plot these points on a graph, and plot the values of different points on this graph, the graph is looking like this. This is point 1, 2, 3, 4, something like this. So all these points are accumulating here, and these bacterial points are accumulating over here. Now we can actually separate these two classes if you're able to draw a line over here. Okay, so that is how LDA is actually separating the classes. Now to just compare the PCA with LDA, and again, so this is the PCA equation, the first principal component equation. Now from this, can you say me what is the first eigenvector? I'm saying this is the PCA, the principal component 1 equation that I have got. Now can you tell me what is the eigenvector of this principal component? Eigenvector of this principal component PC1. Hello, are you able to hear me?
Yeah.
Okay, so I'm just asking what is the eigenvector of this principal component 1? So the eigenvector is just minus 0.71 and 0.71, right? So how do we get the principal component 1? We take the eigenvector and then multiply with the dimensions that we do have, right? To get that equation. So this will be the x and this
Yeah.
will be the y. So 0.71 into x plus 0.71 into y. So that will be the eigenvector in case of PC1. Similarly, if you get the LD1 for this particular data, and if you plot using this equation, we are calculating the PCA scores And we also calculated the LDA scores based on this equation. And then we plotted those 2 points. And this is how they actually look like. So this is the result of PCA. PCA is not able to actually group the or able to effectively classify the classes. Okay, it is just trying focusing on finding out the variance in the data. Okay, it will just try to find out the direction which has the most variance, but it don't have the capability to classify the classes. If you look at these scores, all of them got mixed. But if you use this LDA equation and plotted these graphs, we were able to effectively separate the classes as well. Not only the variance in the data, but we were also able to separate the classes effectively. Okay, so that is how actually LDA works. LDA's main goal is to um, find out or classify the classes in the data. Okay, and also based on the discriminant scores, it will also have it also has the capability to do the dimensionality detection. And now the only goal is we know how to find out this equation PC1. It is just calculating the you know eigenvectors of covariance matrix. Now in today's class, our main goal is to find out or learn how to find out this equation for linear discriminant analysis or linear discriminant scores or discriminant scores, whatever it is. So you have to if you are given with a data set, you should be able to come up with these equations like for PC1, PC2, PC3, how we calculate the eigenvectors, I mean the principal components for a given matrix or given data matrix using PCA to do the dimensional direction. Similarly, we should know how to calculate the discriminant score equations or linear discriminant score equations for LDA. Okay, understood what is that LDA is trying to achieve? It is just trying to achieve the directions where it can effectively classify the classes effectively. Okay, it can be 1 dimension, 2 dimension, 3 dimension. It comes up with those number of dimensions. Okay, so hope you all understood what is the intuition behind or the goal behind LDA, linear discriminant analysis. Is that clear?
Yeah.
Okay, so going back to this particular equation, so how we are trying to construct the objectives of LDA here. What are the key objectives of LDA and how LDA is going to achieve that data? Okay, so just look at these two diagrams. Now the main goal is to separate these two classes. Okay, if it is a two-dimensional data set where we have two different classes, we are just trying to classify them and group them together. Group the similar classes together is our goal. Okay, now the first statement says the mean of the group mean should be large. Okay, or in other words, you can say you want to maximize the distance between the group means. So this is group 1, this is group 2. And now what we are trying to, the first goal of LDA is to maximize the distance between the means of the groups, right? So if we maximize the distance between the groups, what happens? The classification will get better. If the distance between the mean is less, they all are merging again, right? They all are coming close to each other. If the I mean, if the distance between the group means is low, all are coming down and are merging with each other or overlapping each other. But when we maximize the mean between the group, I mean, if we maximize the group means, so the means are going away from each other, and those points, I mean, the relevant points will always be try to be close to the mean. So as much as we maximize this mean, uh, we have that much probability to accumulate the similar groups, right? That is one of the goals. So do you agree that if you maximize the distance between the group means, this is group 1, this is group 2, if you maximize the distance between these two group means, we can achieve our goal, right? Yes or no? Hello? Hello.
Yeah.
Yeah. So we have to maximize the distance between the means should be one thing. Second thing is you have to minimize the variation within each category. What is the variance? Variance is nothing but the spread of the data from the mean, right? So if the spread of the data from the mean is large, let's suppose if you take this particular group, let's take the green group. Okay. So if you take this particular group, if the here now just tell me this is diagram 1 and this is diagram 2, in which diagram we have maximum group variance, I mean variance of each category, where the variance of each category is maximum. This is category 1, this is bacterial category, and the orange is virus category, right? So in diagram when we are comparing diagram 1 with diagram 2, where we do have maximum variance of each category, just look at each category, not the whole data. Or else let me ask like this: the variance is more for bacteria in diagram 1 or diagram 2? Where is maximum variance for bacteria? Where is maximum variance for bacteria? Is that more in diagram 1 or diagram 2?
1.
1, right? Why?
Because here the points are spreaded more, right? So
Yeah. So the from the mean, we have more spread in diagram 1. If you look at this is the mean of bacteria. So spread of the data is more here. And if this is the mean in diagram 2, the spread is very less here. So the variance is less in diagram 2 when compared to diagram. What about virus? So you know for bacteria it is number 1. What about virus?
virus also 1 only. 1 also.
Virus is also 1 only.
1.
So for virus also the variance is more in 1. Now, if you understood where the variance is less, now tell me our goal is to accumulate the similar categories, right? Now what we have to do, we have to minimize the variance or maximize the variance bit in each category, within each category. To achieve a goal, should we minimize the variance within categories or maximize variance within categories? So
We
yes,
should will
yeah, we should.
minimize.
We should
Mi-
minimize the variance, right? So this is minimum variance within category. This is maximum variance within category. Just look at the diagram where the similar groups are accumulated in this diagram 2 or diagram 1. In 2, we have the groups class. I mean, similar classes are grouped together. So to achieve a goal, we have to do two things. One is maximizing the distance between the means of each category. Okay, so this is the mean of first category and this is mean of second category. As the distance between these means are increasing, the similar categories are separated effectively. When the mean is less, they're overlapping each other. So this is not what LDA is trying to achieve. This is what LDA is trying to achieve, right? So the first objective of LDA is to maximize the distance between the means of each category. Okay, the mean of each category, the distance between the means of each category has to maximized. Along with that, even if the mean is maximized, if the variance between within category is large, again there is an overlap. So what it is trying to do is not only maximizing the mean distance between the means, it is also trying to minimize the within category variance. Okay, if even if you maximize, just look at this, even if you maximize the means, something like this, If the variance is large, there will be an overlap. Okay, so we need both of them to happen at the same time. Okay, if both of them don't happen at the same time, you cannot achieve the LDS goal. Let's suppose if I take this particular diagram, and let me get this. If I take a particular diagram, something like this is the diagram, and if I maximize the means of both the data points, I mean, if even if I maximize the distance between those two means, which is mu1 and this is mu2, even if I maximize this, if the variance between the data points is large, there will be an overlap, right? So if the variance in the data is large, this is, let's suppose this is for the group one, if the variance is large, and if I take an example for group two, um, if I take the example for group 2, even from mean, so if the spread is large for group 2, then there is an overlap, right? So we are not able to effectively classify the groups. There is an overlap for both the groups. So along with maximizing the mean, we also have to minimize the variance. Minimize the variance in the sense the spread of the data points from the mean also has to be minimized. Then only we will be able to achieve our goal. Okay, so the first thing is maximizing the distance between the means, and the second thing is minimizing the variance, minimizing the within category variance. Okay, so that variance is called as scatter when coming to LDA. Scatter is proportional to variance. It's just an a scalar multiple of variance. Okay, understood the objective of LDA, how LDA is trying to achieve that particular goal.
Yeah.
Okay, so now just I'm putting forward this objective into an equation now. So let's suppose for the category 1, the mean is mu, and for the category 2, the mean is mu. This is in which is in red color. Now what we are trying to maximize, we are trying to maximize the distance between these two means. So we are actually trying to maximize the distance. Distance is nothing but this point minus this point. So to avoid that negative value for this difference, we are taking the square. All right. So we don't want the objective function to be negative. Okay. So we are just squaring this. Okay. So that is square scalar multiples will never impact our analysis. Okay. It's just multiplying the value. That's all. So as this is also a scalar value, it is not going to get impacted. Okay. That is first thing you have to understood. So you just to avoid the negative value for this particular mean. So if this is less than this, if this is less than this, I mean, if red mu is greater than green mu, we are going to get a negative value. So if we don't apply square to it, we will still get a negative value. We don't want to have a negative value, which actually impact the analysis. I mean, it actually gives a wrong interpretation. So we never want to actually go ahead with the negative values. So we always want to go with the positive values. That's the reason we just squared it. And the scatter of categories, scatter of within categories is represented by S square. Okay, where LDA calls scatter, minimizing the variance is its objective, and that variance is called as scatter in when it comes to LDA, and that is represented by S square. Okay, within each category. So this is the scatter of category 1, and this is the scatter of category 2. So now our objective function becomes this way. If we accumulate both the objectives, so that let me call that as J of W objective, that is mu minus mu1 minus mu2. Mu1 is the mean of first category and mu2 is the mean of second category by S1 square plus S2 square. So this is what the objective function is. Why this S1 square plus S2 square came in the denominator and this came in the numerator. Now this objective becomes a maximization problem or minimization problem. Do we need to maximize this objective or minimize this objective?
Maximize.
We have to maximize this because when we maximize this, what happens? So just look at this. This is the distance between the mean. We want to maximize this. So when you maximize this, this will get maximized. And what is that you have to do? You're trying to minimize the scatter. Minimizing the scatter will obviously improve this whole value, right? So minimizing the denominator will improve this particular value. Let's suppose 5 by 2 is equal to 2.5. 5 by 1 is equal to 5. So if the denominator is decreasing, the overall value is increasing. So the overall value we are trying to maximize. Only when you maximize this j of w, you are going to achieve this goal in turn. So to maximize this value, you have to, I mean, it is vice versa. So uh, when you maximize the distance between the means and minimizing this, minimizing the scatter of within category, what you will get the maximum value for j of w. So when you maximize j of w, you're going to achieve the goal. Okay, so finally the objective function will become maximization problem. Now the whole thing that you have to do is, what you have to do to get the max to solve a maximization problem, and what is the goal now? Your goal is to find out the direction w. Okay, the direction w, which is effectively separating the categories in the given data set. Okay, so that is what your goal is. Your goal is to find out the direction of w. Okay, so that is your goal, and you also have got the objective function now. Now you just have to solve this objective function. How do you solve this objective function? You have to take the derivative of this objective function and equating that to 0. And once you equate that to 0, you will get a w value, and that w value is something which will give you the direction which effectively separates the categories in the data set. And also you can reduce the dimensionality based on different criteria, based on the chosen values. In PCA, you have chosen, I mean, if you get 3 eigenvalues, you can just restrict to just one eigenvector, and you can transform all the data to one direction. Okay, if eigenvector 1 is actually covering 90% variance in the data, you can just go with one dimension, because your critical point is just to cover 85% of variance in the data. So 90% is more than 85%. So you will just come up with one direction. So you reduce three-dimensional data to one-dimensional data. Similar way, based on a similar value like eigenvectors, you will choose how many dimensions you have to retain in the data to achieve this particular goal. Okay, now you are, as you know, the main objective here is to find out just this just to solve this objective function. Now we constructed objective function, the next goal is to just solve that objective function. Okay, now let me tell you the way to get this objective function solved. Okay, let me add a slide here. Think it need two more slides here. So we try to solve this LDA objective now. Okay, so that is a goal now. Right. So let's go back, understand. Let's understand solving the objective here. So what is the objective now? The objective now is j of w. I call that as j of w. The objective now is what we are saying. Let's call that as uh, mu1. Instead of mu1, I'll call that as m1, which is mean of the category 1 and mean of the category 2 whole square by scatter of category 1 plus scatter of category 2. Okay, so this is our objective function. So this is numerator and this is denominator. Let's just go with numerator, m1 minus m2 whole square. Okay, so let's just try to solve this. Okay, and then we can come back understanding the denominator. So what is m1? Mean of the points, right? right or not? So
Yeah.
let's say we have two categories. Let's understand this very carefully. What we are doing in LDA, we have two categories in the data, something like this. Okay, this is category one. This is our category one. That is, I'm just drawing the diagram that we have seen earlier. We have seen two different categories, and I'm just trying to plot those categories here. Okay, so that is category one, and the other category is this. Okay, so this is category two. I just want to differentiate that with another color. So once you understood this objective function solving, you will find out few things, and then the calculations would be little very much easier. Okay, so the objective function is something that which is important. So this is category two. Now what we are trying to do is find out this W, right? Now what we are trying to do, we are trying to find out the direction W such that what we are trying to do later to that, we are trying to find out this W, and then what we are doing, we have projected these points onto this W, right? We have projected the points onto W. The projection of points onto this W is nothing but we are projecting all the points, and then we have found out the mean of those points. Similarly, we have projected all these points onto this LW, and we found out the mean of both the points. What is the mean of point 1? We call that as M1, right? So the mean of all these points is M1. That is what it is said. The mean of all the points is M1, and the mean of these points is M2. Okay, that is what we have seen as mu1 and mu2 in the other diagram. Okay, so this is mu2, or M2. That is what we have seen. So how we are actually discriminating them, if you just go back to this previous slides, what we have seen there, we have seen the things that we have what that we are discussing. So we projected these points onto the new dimension, and these are the means of the projected points, and we are trying to maximize these means, right? So if you go back here, what this is saying, so it is saying like just find out this D1 and then project the points onto the D1. Okay, so we are just trying to project those points onto D1. So this is where we projected, right? Look at this. All the points will come down to D1. So we projected those points, and the mean of these 2 points has to be maximized. Only when we maximize, so this particular line is equal to this one in the next screen. Okay. So this is where you're seeing that data projected onto D1. So now we are trying, the objective is to maximize these means and minimize these scatters. Okay. So M1 is the projected mean of all these points. Okay. M1 is the mean of all these projected data points. M2 is the mean of the projected points. The mean of this, the projected mean, I would say, of these data points. Where it is projected onto W or D1 or linear dimension, or where the dimensionality score is good. Okay. I'll call the direction as W for now. Now I'm also taking this now. So I have data set D. It has two categories, right? The first category is D1 and the second category is D2. Okay. Number of points in this is called as N1, and number of points in this is called as N2. Okay. Let's suppose we have N1 points here and 2 points here. Okay. N2 points as one category. N1 points as N category, N2 points in category 2. Okay, I have this data set divided into two categories. So if you look at this previous matrix, it has virus and bacteria. So I just differentiated this data as D1 and D2. And now M1 is the mean of these points. Okay, M1 is the projected mean of these points on W. We are just trying to find out this W now. That's our goal. Okay. So M1 is the projected mean of the data points on this W. M2 is the projected mean of, what is that? M2 is the projected mean of this category data on W. Let's suppose if I take this point as x1, what is this point will become? X1 is the projection of xi is the, let's suppose xi cap is the projection of xi on W. Then what does xi bar will become? What does xi bar will become? That is xi dot W by W into W, right? Into W bar, which is the direction. Is that right? Right or not? The projection of a point onto vector W. Hello. Yeah. So now let's think W as a unit vector for now. So if W is a unit vector, W dot W will become 1. Okay. So xi bar will, if W is a unit vector, we are just interested in just the direction here. Okay. So let's suppose W is the unit vector. Why we are just interested in only the direction here, but in PCA we are also interested in the variance. We are trying to find out the most variance in the data. That is an objective, but here the objective is not related to the variation. It is just trying to separate the classes. So I'll just take W as a unit vector, so which is completely fine, and it will not be a constant here, because we are not trying to find out the variance covered in the data. We are just trying to classify the data points onto, effectively classify the data points onto lower dimensions. Okay. So now that becomes xi dot W. If I convert this to matrix notation, I would say W transpose into xi can be, this can be written as W transpose into xi, right? So what is matrix multiplication of a point? Matrix multiplication of a point is nothing but, of a dot product is nothing but W transpose into xi. Okay, we can also write as xi transpose into W, but W would be common for both of them, because for these two data sets, I will have W common, so that I will just take the transpose of this, so that calculations would become easy, right? So that is the projection of a point onto W, right? So xi is the point in category 1. When we project that to onto vector W, that becomes W transpose into xi in matrix notation. Now what is M1? M1 is nothing but the mean of all these points, right? If you take the average of all these points, that becomes M1. Okay. I mean, that becomes the group mean. Now that mean has to be projected onto this W. Okay. So let's understand this in this way. Okay. Now there are two things here. The first thing that you have to understand is, okay. So the first thing that you have to understand is, first thing we have to calculate the mean of all these points. Now we are concentrating only on this mean. Okay. The mean of these points would be this, and this projected mean is what we are talking about. This is the projected mean of these points. Okay. The projected mean on vector W of all. So first let's calculate the mean of all these points. What does the mean of all these points will become? Summation of xi belongs to D1, right? Xi by N1. Okay. Do the summation for every point that belongs to dataset D1. We are just trying to find out the mean of dataset D1. So that becomes sigma for every xi that belongs to D1. Do the summation divided by the number of points. So the projection of this mean onto W will be nothing but W transpose, right? So this becomes W transpose, right? So this is the mean of all the points. I'll call that as mu1, and this is the mean of all points mu2, and mu1 m1 is the projection of mu1 on W. So that becomes W transpose into mu1, right? Mu1 is nothing but for every xi that belongs to D1, summation of all these points by number of points, right? So now M1 becomes W transpose mu1, right? Similarly for M2, can I write this as W transpose into mu2, right or not? Can I write M2 as W transpose into mu2? M2 is nothing but the projection of mu2 on W. Projection on mu2 into W will be nothing but W transpose into mu2. Okay. So that's what I have written over here, and we have square on top of it. Till this point, are you clear? Hello. I don't know if you're able to understand this or not. If you don't understand, if you say that, I'll just try to repeat that. If I will not understand that right away, that you understood that or not. Is that clear for everyone?
Yeah.
Yes or no? Should I repeat this again, or you understood this? Hello. So now this becomes, if I take this W transpose as common, I took this W transpose as a common from both these equations, and this becomes mu1 minus mu2 whole square. Okay. So that is what it is now. Now I would like to try write this as W transpose in matrix form. This becomes mu1 minus mu2 whole transpose into mu1 minus mu2 into W. So this is nothing but the square in matrix notation. So A transpose into A is nothing but A square. Okay. So that is how you represent a particular thing in matrix notation. So this is the mu1 minus mu2 whole square. W transpose into W is nothing but W transpose square. It's just equal to W square in matrix notation. So I represented this in matrix notation now. Now what I'll say this is, I'll just simplify this into a different equation now. So that would be this one. So what is that? I'm writing this as W transpose SAB into W. What is SB? SB is nothing but mu1 minus mu2 whole transpose, mu1 minus mu2 whole transpose into mu1 minus mu2. So this is what SB is. Okay. So now this is first thing that you have to actually keep in mind. What is the first equation that we have derived? We derived that SB is equal to, we replaced this equation with SB. Okay. So this is what we have found out SB. So now the numerator is coming down to W transpose SB into W. Okay. So now what is this SB called as? SB is called as between class scatter matrix. SB is named as between class scatter matrix. Between class scatter matrix. Scatter matrix. Okay. So that is called as between class scatter matrix. Understood? So now this, when you say what is the formula for SP, SP is nothing but mu1 minus mu2 whole transpose into mu1 minus mu2. Mu1 is the mean of the category 1, mu2 is the mean of the category 2. Okay. So this is first part of our objective function. Now can I write this? Can I write the J of W as W transpose SP W by S1 square plus S2 square. Okay. So this is our new objective function. Now let's concentrate on the denominator. How does the denominator actually looks like now? We will try to find out S1 square plus S2 square. S1 square, what is this? Is the scatter of category 1, right? That is the scatter of category 1. Okay. What is scatter is nothing but, scatter is nothing but a similar parameter of, you know, variance. What is the variance? Variance is nothing but sigma uh, for every xi that belongs to, for every xi that belongs to D1, how do we calculate the um, mean of all those points? It is nothing but xi minus mu whole square, right? So this is the formula for the variance. But now we are trying to find out the variance of the
1 by
projected
n.
points. Yeah. So as I told you, right, S1 square is not right away variance. Variance is nothing but n multiplied by sigma is the scatter. Okay. So n is again a scalar. Just multiplying by a scalar will never, it just scales the
1
value,
by
but
n there.
it will not impact anything. Just scatter, think of scatter as n into variance. Okay. Variance is denoted by sigma, not something like this. Okay. So that is sigma. So which is like covariance matrix or variance or whatever it is. So n multiplied by this covariance is the scatter. Just remember that. So anyways, n doesn't really matter. It is just a constant. So it just scales the values, but it will not have any impact on the on the things on the analysis part. Okay. So now we know the variance is nothing but xi minus mu whole square. But to which we are trying to find out the scatter, we are trying to find out the scatter for the projected points. So these two will become xi cap minus m1, right? So we are trying to find out the variance for the projected points on W, right? So xi will become xi cap because this is a projected point. Mu will become m1. Okay. So that is how you calculate the scatter. Okay. So we are trying to find out the variance of the points scattered from the mean. Mean would be the projected mean, points will be the projected points. Okay. So this m will become m, this become m. M is the projected of mu, xi cap is the projected point of every point in xi. So I'm trying to write this as for every xi that belongs to D1, category 1, xi can be represented as W transpose into x1 minus m can be written as W transpose into mu1 whole square. Okay. So now this can be written as sigma for every xi, for every xi that belongs to D1. I'm again taking W transpose out and I'm making this as xi minus mu1 whole square. Okay. So again, I mean, this becomes the whole square, not just the square for xi minus mu. Okay, let me just correct that. So this becomes the whole square, square for the whole, square for the whole equation. Okay. So this will become the square for whole equation. So now how can I rewrite this? I can rewrite this way, right? So this becomes, um, so this becomes W transpose sigma xi belongs to di. So W transpose has nothing to do with xi. So I brought this W transpose out and now I'm writing xi minus mu whole square as xi minus mu1 whole transpose into xi minus mu1 into W. Okay. Can I write it this way?
Yes.
Now I'll again rename this as S1. Okay. I'll call this a small s1. That is capital S1, right? So I'll name this a small s1. The middle part is what I'm talking about now. Now I'm going to replace this bigger term with a representation. I'll call this as W transpose S1, small s1, or I'll replace this with something else. Or just for safer conversations, um, what can I'll just make it a small s. Okay, just think of that as small s. Let me erase that. Yeah, so this is the small s and W. Now what is small s? Small s is for every xi that belongs to di, xi minus mu1 whole transpose into xi minus mu1. Okay, that is the simplest form of representation of s1 square. S1 square is equal to W transpose small s1 W. Now can I write S2 square as W transpose small s2 into W? Can I? The same thing applies, but xi belongs to D2, W transpose into W transpose of xi minus W transpose into mu2, because we are talking about category 2. So, and if you do the same calculations for that, it becomes xi belongs to D2, xi minus mu2 whole transpose into xi minus mu2. So I am writing the small s square as this way. Now, what is small s square? You apply the same thing again. You will not change any, I mean, this part will not change for 2. So the small s2 can be written as for every xi that belongs to D2, xi minus mu2 whole transpose into xi minus mu2. So this is s2 and that is s1, right? Understood still this point?
Yes.
Now, what does s1 square plus s2 square become? S1 square plus s2 square is nothing but W transpose small s1 into W plus W transpose small s2 into W. Now I can rewrite this as W transpose into small s1 plus small s2 into W, right? So I'll again replace small s1 plus small s2 with SW, that is equal to small s1 plus small s2. Okay, so s1 formula is this, s2 formula is this. So when you apply this, when you do the summation, it converts to this, and I'm replacing this whole term with SW, which is called as, now I name SW as, what is SB? What is called SP? What we named SP as? What we named SP as? Between class
But
scatter matrix. SP is between class scatter matrix. SW is within class scatter matrix. So we are trying to do this within classes, right? Within class scatter matrix. Within class scatter matrix. Okay. Understood? Within class scatter matrix. Now I can write the whole. What is that? Now I can write the whole equation as this way. Right? Let me take another slide. What is the new objective function for us now? The new objective function for us now is S of W, I mean J of W is equal to, what is that? J of W is equal to W transpose SBW, W transpose SWW. What is SP? What is SB? What is the formula for SP? SP is nothing but mu1 minus mu2 whole transpose into mu1 minus mu2, right? So I'm writing SP as mu1 minus mu2 whole transpose into mu1 minus mu2. That is what SP, where mu1 is the mean of category 1. What is mu1? Mean of class 1 or category 1. What is mu2? Mean of class 2. Mean of class 2. Now what is SW? SW is nothing but S1 plus S2. What is S1?
Scatter of class.
What is S1?
Scatter of class 1.
Yeah. Within class scatter matrix is SW. Within class scatter matrix, when I'm just talking about the formula, for the formula for this is for every xi that belongs to class 1 or dimension 1, or D1 is the data that we have derived. So this is xi minus mu1 whole transpose into xi minus mu1, right? That is what S1 is. What is small s2? Small s2 is nothing but sigma of summation of for every xi that belongs to D2 xi minus mu2. Mu2 is nothing but the mean of all the data points in category 2 whole transpose into xi minus mu2. So this is what S1 and S2. Once we find out that, we just have to do the summation for them to get SW. So this is how we calculate SB and SW. Okay. Now we still haven't solved the objective function. We just simplified this objective function. So this is still our objective function. Now to solve this, what is the JW? Your problem is maximization problem. You have to maximize J of W, right? So to maximize this, what you have to do? To maximize this, what you have to do?
Numerator minimum.
Hmm?
Denominator minimum.
No, we talked about maximization and minimization problems, right? So you have to find out the W such that this will be the maximum. I mean, the maximum value, the critical value finding maximum value or not. How do you actually find out that? Doing a maximization problem. This is optimal problem, right? This is optimization problem. This is optimization equation. To maximize this optimization equation, what you have to do? Do you remember that maximum, finding a maximum minimum values? We have seen that first derivative, second derivative, and finding the maximum values and minimum values from the critical points. What we have done to maximize the objective function of our optimization problem, objective function, this can be called as objective function also. What we have done in PCA, we have taken the derivative and equated to 0, right? So now the objective function is something like this. You have to take the derivative of that function and equate that to 0. So this is our objective function. What is our objective function? J of W. J of W is nothing but W transpose SP W by W transpose SW W. To maximize this, we have to take the derivative and equate that to 0. So when you take the derivative, what is the chain d by df x of x by y? Y into derivative of x minus x into derivative of y. That should be equated to 0, right? So this is the derivation for this. So this becomes denominator into d by dx of numerator minus numerator into d by dx of denominator by denominator. Anyways, denominator will be getting multiplied with 0 and thus that will be 0. So now if you take the derivative of this, W transpose into W is nothing but W square, right? So W square will become 2 into W. So 2WSP. So the derivative of this will become 2SP into W. Okay. So anyone have this question of why W transpose into W is W square? I think I have already shown you by taking an example of two vectors and then I did a transpose, multiplied that, and we got the same value. Do you agree that W transpose into W is nothing but it's a matrix representation that would be equal to W square,
Yeah.
right? So W square, when we differentiate that with d by dw, that becomes 2W, 2 into SP into W. So this is already there, and the derivative of this would become 2SW into W, right? That would be equal to 0. Now, what this actually happens is, to just simplify this, um, what I'm trying to do here is, uh, you're just trying to find out this thing, right? What is that? I can put it this way. So take this equation. Now, what this is showing up like, take this value to the other side, okay? And take this value to the other side, and you will get an equation something like this. So just look at this. W transpose SW into W into 2SBW is equal to W transpose SPW 2SWW, right? So 2 and 2 will get cancelled, and just look at this equation. I'm taking this to this side. I'm taking this whole part to this side. And now what does this become? SPW is equal to W transpose SBW by W transpose SWW into SWW, right? So this is the equation that we're getting. Now, what is our objective function? Is this same as our objective function? So
Yeah.
these two are same. So now I'm going to rewrite this as, this is the final notation. Just carefully observe this. Here is the conclusion of what we are studying now. So now I can rewrite this as SPW is equal to J of W, which is objective function, because I'm replacing this with objective function, into SW of W. Now, what is SB? SB, what is the name of SB? What is the name of SB? SB is between class scatter matrix. SW is within class. Within class scatter matrix. So LDA, two terms, within class and between class. We are trying to maximize the distance between the means of classes between classes, right? The best word would be maximize the distance of means between the classes and minimize the variance or minimize the scatter of points within class. Okay, within class and between class is what the objectives basically talk about. Now SPW is equal to J of W into SWW. Okay. Now carefully understand here. We are coming down to conclusion of how do we find out the W. Okay. Do you now just understand this? W transpose SB into W. Okay. So SB WW. Okay. Now just understand how what does this value actually looks like. Okay. This value will be equal to a scalar. Why I'm saying that is, mm, Do you remember that X transpose A into X? Do you remember that positive semi-definite matrix? Positive semi-definite matrix. Can someone say me what is a positive semi-definite matrix? Whether a matrix is positive semi-definite or not, what you will do?
Eigenvalue should be positive and symmetric matrix.
Hmm. Have you seen anything similar to this when we are studying about positive semi-definite matrix? X transpose A into X, something of that sort. Quadratic form of a matrix. Have you seen that?
Uh,
Yes or no?
X transpose AX is equal to 0.
Is equal to 0 or anything else?
Less than or equal to 0.
Less than or equal to 0?
Greater than. Greater than or equal to 0.
Greater than or equal to 0, right? So we studied that,
Yeah.
right? For any non-zero vector, the resultant of the quadratic form X transpose A into X is non-negative, right? Is this looking similar to this?
Yeah.
So will this be a scalar value or vector value? Will this be a scalar value or a vector value?
Uh, Vector maybe.
Vector.
Scalar matrix.
This is scalar value, right? You are saying X transpose A into X for any given matrix, X transpose A into X is greater than or equal to 0. So you're comparing that with a scalar value. So that right side would also become a scalar value, right? For that to happen, SP has to be a positive semi-definite matrix, right?
Yeah.
So So at least just try to compare these two. X transpose A into X is just greater than or equal to 0. So on right side, you're comparing with the scalar value, whether it is greater than or equal to 0, right? So the left hand side should also be a scalar value, right? Then only you can compare. When the other side cannot be a vector when you're comparing with the scalar on the right side, right? You're saying X transpose A into X is greater than or equal to 0. So this can be anything like 5, 4, 3, 2, something like that only. But it cannot be something like 2i plus 3j. It cannot be a vector, right? You cannot compare a vector with an scalar value. So this also has to be a scalar value. So you agree with that? Hello. Do you agree that W transpose SP into W is a scalar value when SP is a positive semi-different matrix?
Yeah.
So this, when this is scalar, what is scalar? Scalar means a constant value, an integer value. It cannot be a vector or a complex number. And when you say positive semi-definite matrix, all the values has to be integer values only. We already studied that. So, so this also has to be a scalar value. Okay.
Yeah, scalar.
So this is a scalar value, this is a scalar value. So J of W would be a scalar value in total, right? J of W will be just a number. Yes or no?
Yes. This scalar.
I can keep this for you in another way. Maybe if you're not able to accept that, let me say you this thing. Let's go back to the formula of SP. What is SP? SP is mu1 minus mu2 whole square into mu1 minus mu2, right? So let's take the example of 2 by 2 matrix. Okay. So let's suppose what for a two-dimensional point, you will get a two-dimensional mean, right? Yes or no? For it, I mean, for a two-dimensional point, what would be the mean? So if this is my data set in two-dimensional, how does my mean look like? How does my mean look like? Mean look like x1 x1 comma x2, right? Right or not? Is that right or not? How does a mean of two-dimensional data looks like? So dimension of a two-dimensional matter will look like d comma I mean x1 comma x2, right?
Yes.
How about three-dimensional?
X1 comma X2 comma X3. 3 pointers ఉంటుంది.
Yeah, it will be three-dimensional.
Yeah, 3 points X1, X2, X3.
Okay. Yeah, so it would be it would be three-dimensional data, right? So number on based on the number of dimensions, it would always be d by d matrix for this, right? Mu1 minus mu2 is nothing but difference between the means of different data points. So each dimension would be the number of equal to the number of dimensions in the data, right? So if it is two-dimensional, it would be 2 points. If it is three-dimensional, it would be 3 points. Something like this, right?
Yeah.
Hmm. All right. So just understand that would be an d by d matrix, right? One second. Right. So this would become d by d matrix. So mu1 minus mu2 for this would be d by d matrix basically. Okay. Um, how would I put this? So do you able to analyze this? I mean, accept this as d by d matrix or not? Mu1 minus mu2. Will this be d by d?
Yeah.
This will be d by d, right?
Yes. Hello.
Are you thinking of it or just waiting for the answer? Will this be d by d or not?
Yeah, D by D.
D by d only? Mu1 minus mu2 will be d by d. Is that right? I don't know. I'm still waiting for the other answers. Will this be d by d mu1 minus mu2? What will be the dimension of that particular vector? You're not able to interpret it. Just when you're asked to actually understand this, you have to actually go with some data points. Okay. So let's take the example of two dimensions only. If that is 2 by 3, 2 comma 3. Okay. If that is 2 comma 3, this is the mean of a two-dimensional, right? So a 2 comma 3 point would be represented in cardinal form as 2, 3. So this is mu1. Mu2, I can take it as 3, 2, something like this. So this is mu2. So mu1 minus mu2 will become again something like minus 1, 1, right? So what is the dimensionality of this? This is d by 1, right? If it is three dimensions, I mean, it is 2 into 1. If it is three dimension, it is 3 into 1. If it is d dimension, d into 1. So mu1 minus mu2 will always be 2 into 1. I mean, d into 1. Mu1 minus mu2 will be d into 1. So you know mu1 minus mu2 is d into 1. What is the transpose of mu1 minus mu2? What is the dimensionality of that? So you know mu1 minus mu2 as d into 1. What is the dimensionality of mu1 minus mu2 whole transpose?
1 into 2.
So it is 1 into d, right? So if we
Yeah.
get 1 into d into d, what will be get what we will get as b? So mu1 minus
1 into
mu2
D.
whole transpose is 1 into d, and mu1 minus mu2 is d into 1. What will be the value of this now? Will be
1 into D.
1 into d,
1 into 1.
1 into 1. It's a scalar. Now, what is the dimension of vector w? What is the dimension of vector w? What is the dimension of vector w? So what is the dimension of vector w? I don't think you're understanding anything of what I'm talking. So w is a unit vector, right? in this plane, in a 2D plane, any unit vector in 2D plane or any vector in 2D plane will be represented by this way, right? This is a point, this is a vector. If I represent 2 comma 1, this is the representation of that vector 2 comma 1. So by tomorrow I'll be completing the first part of machine learning out of 4 parts. And in the coming week, someday around Thursday or Friday, you will have an exam. Okay, you will all attempt on all the concepts that we have learned so far. There will be an exam and you have to actually attend that for sure. So I'm not sure if you're understanding this or not. These are all simple things. So W is a vector. That is what you're trying to find out. So that will have a dimension of D1. Okay. If it is d-dimensional data, d-dimensional, the dimensionality of that would be, d into 1. So if it is two-dimensional, the point will be something in the cardinal form of that is 2, 3. If it is three-dimensional, the cardinality of this 2, 3, 4. If it is d-dimensional, d into 1. So the W transpose is 1 into d. Okay. So W transpose is 1 into d. SB is 1 into 1. W transpose is 1 into d. SB is 1 into 1. And W is, what is the W? W is d into 1. So can we multiply these two matrices? 1 by d with d into d, 1 into 1. Can we multiply those two?
Yeah.
Can we? 1 by d into 1 by 1. Can we multiply a matrix of dimension 1 by d with 1 by 1 matrix?
No.
You cannot
So
multiply.
constant.
So
Constants.
now this is the mistake that we have done in the derivation. Okay, the mistake is I was able to just find out just by understanding the next one. So this cannot be the transpose. Okay, so SP formula will stand for, okay, so this is not right. The transpose goes here, mu1 minus mu2 whole to transpose. Then what does this become? So this becomes d by d matrix then. This becomes d by d now. Okay, so mu1 minus mu2 we know that as d by 1. What is the dimensionality of mu1 minus mu2? Mu1 minus mu2 is d by 1, right? So mu1 minus mu2 is d by 1. Mu1 minus mu2 whole transpose is 1 by d. So that becomes d by d matrix. So when this
Divided.
is d by d matrix, 1 by d into d by d can be multiplied. Okay, into d by 1. So this is 1 by d, this is d by d, this is d by 1. So this all becomes 1 by 1, which is a scalar
1
value.
by 1 minus.
So that is what 1 by 1 is nothing but a scalar value. The same applies for W transpose SW into W. So this has to be D by D matrix. So for this to be D by D matrix, the transpose has to go to the next term. This transpose has to go to the next term. So just these are all will change to transpose to the second term because we want D by D matrix, not 1 by D. Okay. So when you're deriving this, look at this. When you're deriving this particular value, you're writing mu1 minus mu2 whole square as mu1 minus mu2 whole transpose into mu1 minus mu2. So x square can be written as x transpose into x and x into x transpose. It can be written in both the ways. But based on the previous vectors and next vectors, we have to decide what you have to choose. In this case, we want this to be d by d matrix. So the transpose should go to this one. Okay, because this is W transpose is 1 into D. So if you want to multiply with this particular matrix, this matrix has to be D by D. Okay, then only you can perform the matrix multiplication. So this should change to mu1 minus mu2 into mu1 minus mu2 whole transpose. The same applies for SW as well. SW, this is 1 into D. W transpose is nothing but 1 into D. So this has to be D by D. For this has to be D by D. This has to be transpose has to go to the second term. Transpose has to go to the second term. Okay. So then now you find out that this is a scalar value. W transpose SB into W is a scalar value because SB dimension is D into D. W transpose is 1 into D. W is equal to D into 1. So that becomes 1 by 1 and this is also 1 by 1. So this whole thing will become a scalar value. Okay. So now the new things would be this one. Okay, so this is the scalar value. Now we found out that j of w is a scalar value. That's what we have found out, right? So as this is a scalar value, I'll replace this with spw is equal to lambda sww. Okay, I'm rewriting this as I'm taking this or multiplying both sides with SW inverse. I'm multiplying both sides with SW inverse. So this becomes SW inverse of SP into W is equal to lambda into W. Okay, SW into SW inverse will become 1, right? So SW into SW will become 1. Let me take a new slide. So let's write everything back again. So now what we have got SW inverse into, now we have got SW inverse SP into W is equal to lambda W, right? So this is what we have found out. Now we know AW is equal to lambda W. You know this equation. What is this equation? What is this equation is? Where have you seen this equation? AW is equal to lambda W. Where have you seen that equation? What is the equation that you have used to find out the eigenvectors?
AX is equal to lambda.
I is equals to lambda.
So AW is equal to lambda W. W is the eigenvector, right? For matrix A. W is the eigenvector for matrix A. Okay. So this is the equation of eigenvector decomposition. So to find, if you are seeing something like this, lambda is the eigenvalue, W is the eigenvector of matrix A. So now the goal is to find out the W, right? You have to maximize the W. So to maximize the W, the only thing, it is nothing but W is the eigenvector of, W is the eigenvector of SW transpose SB. So if you find out the eigenvectors of these things, and that will give you the W value. So if you want to maximize the W, you have to take the largest value of the lambda. So the linear discriminant analysis falls down to finding out the eigenvectors for SW inverse SB. And how do you calculate SP? What is the formula for SP? Between class scatter matrix, it is mu1 minus mu2 into mu1 minus mu2
Into
whole transpose.
transport.
And what is SW? SW is nothing but S1 plus S2. So what is S1? This is small s1, small s2. What is S1? Summation of, for every xi that belongs to D1, xi minus mu1 into xi minus mu1 whole transpose. So, we interchanged this in the last time, so that's wrong, because we have seen why that is wrong. We want SB to be a D by D matrix so that we will be able to multiply with this direction vector, which is W. So S1 is this. What about S2? S2 is nothing but sigma xi that belongs to D2, xi minus mu2 into xi minus mu2 whole transpose. So this is S1, this is S2. And using these two, we calculate SW and we calculate SP using these two things. And then we come up with, we can calculate SW inverse to the power of, XW inverse into SP. You also know how to calculate the inverse of a matrix. You know how to calculate SP, just a multiplication. And then you have to find out the eigenvectors of these. And the eigenvector associated with the largest eigenvalue is something, the maximum direction, the best direction for W, or the best direction that differentiates the classes in the data set. Okay. So this is all about the proof of, you know, linear discriminant analysis. Understood? I don't know, but you have to understood, revisit, go through the video once again. But I think I should conduct an exam to understand where you are actually. So I'll go for today. I think the first part of machine learning. So machine learning course is divided into 4 parts. We will be completing with first part today out of the 4 parts. By end of tomorrow, you will get almost. We will be completing with the first part. So we will be left with 3 more parts. I would say in our journey of 100%, so machine learning falls down to somewhere around 20% of our journey. Okay, so 20% of this journey with machine learning. So rest of would be like we are going to learn about deep learning, and we are also going to learn about artificial intelligence, RAGs, LLMs, and all that stuff will be there. So out of 100% of the total course that we are going to learn till next May, 20% would be the machine learning stuff. Out of this 20% machine learning stuff, 10% would be theoretical, 10% would be programmatical. Okay, out of this 10% it is divided into 4 parts. Okay, so somewhere around each part falls under 2.5 percentage. So by tomorrow end of the day, we are going to complete 2.5 percentage of our 100% journey. So this is where you will face an exam. You just have to solve everything theoretically. I'll give you the question paper. We can connect someday in the evening, sometime in the next week. And on live we will all come on to cameras. I'll display the question and you have to answer that, and by end of the exam you just have to submit all your answer sheets to me. Okay, that's how it's going to be. And it would be just 2 hours, I think. Let's go for 2 hours exam and see how far you are with this 2.5 percentage. It's not an easy journey, and if you want to do something big you have to try hard. Again, I'm saying you are just spending 2 hours or 3 hours. I'm spending around 12 hours, proportional, 4 times proportional to effort that you're giving. Okay, just think from my side, and then evaluate the effort that you're keeping for yourself. With that all in place, so by tomorrow end of the day, I would say we are going to complete 2.5 percentage in our journey, which is the basic stuff. So it takes time, but in future we will be little faster. As you understood all the concepts very clear, the rest of the stuff would be just programming, and it is, I am pretty sure if you understood that would be really easy. So this 2.5% is difficult. When you come to the next session, where I think we go to item set mining. So the best example for that is Amazon stuff, right? So we recommend the products to the customers based on other customers' behavior in the stores. Okay, that is what item set mining is. So we are going to complete the item set mining. That's what we are going to learn, that it's a simple math. This is the difficult part, I would say. This 2.5% is something which is difficult when coming to machine learning stuff. We have some difficult concepts here and there, but not, they won't be this much difficult. But this 2.5% is base, and it is very important too. So let's take an example of a matrix, and let's see how we can solve that how we can solve that matrix using linear discriminant projection. So we want to separate those two classes, right? So now I was given with two classes. One is class 1 W1, and the other one is class 2, which is W2. Okay, now this is the class 1 which is given to us. This is class 2 which is given. So we are given with two classes. So we want to merge those two classes into one matrix. So how does that look like? It looks like a simple matrix: 4 2 2 4 2 3 3 6 4 4 9 10 6 8 9 5 8 7 10 8. Okay, so this is the matrix that is given to us. So this would be the complete matrix. So out of this complete matrix, this falls to be class 1 and this falls to be class 2. Okay, so this falls to be class 1 and this falls to be class 2. Now we are actually we have drawn that in this coordinate system. So what is the 2 comma 4? So what is x1 here? This point is 2 comma 3. So this point is 2 comma 3. So this is the one. This is 2 comma 4. This is 4 comma 2. This is the point. And this is 4 comma 4. And this is 3 comma 6. So these are all x1 coordinates and these are all x2 coordinates. Now we want to differentiate these two by drawing, by finding out that projection. Okay, discriminant scores. So given this matrix, how do we calculate this stuff? So first thing first, we are trying to calculate SW. SW is nothing but S1 plus S2. What is S1? For every X that belongs to D1, Xi minus mu1 into Xi minus mu1 whole transpose, right? What is S2? S2 is nothing but for every xi that belongs to D2. What is D1, D2 here? They called it as class 1 and W1 and W2. So D1 is class 1, D2 is class 2. So they named it as W1, W2, whatever the name is. So xi minus mu2 into xi minus mu2 whole transpose. So this is what we have to calculate to find out SW. So they calculated mu1 and mu2 first. Mu1 is nothing but sum of the points by number of the points. What are the points? For the first, it is 4, 2, 2, 4, 2, 3, 3, 6, 4, 4. So these are the points given for x1. So sum of all these points, sum of all x coordinates, sum of all y coordinates by number of coordinates. Okay, by n. So that becomes 3 by 8. Mu2, the same formula, sum of all points on class 2 by the number of points in class 2, which would be this one. And now for every xi, you have to subtract the mean. So this is x1, 4, 2, minus mean, second point minus mean, third point minus mean, fourth point minus mean, fifth point minus mean. So when you do this multiplication, you're getting this value. Okay, it is just xi minus mu1 into xi minus mu1 whole transpose. So that is why it is squared. Okay, square is nothing but xi into x transpose. As this is two-dimensional, they are just doing a square of that. That's all. You know how to calculate the transpose of a matrix. So let's suppose if I'll just take the example of this. What is xi minus mu here? Xi minus mu is 1 minus 1.8, right? Into transpose would be 1.8. Why is this 2 into 1? So this has to come this side actually. So it would be scalar value 1.8. No, this would be the same because we need S1 to be a D by D matrix, right? So that is the reason. So it cannot be a scalar value, it has to be a matrix. So that is what it is. So I'm going to erase this. So this is going to be, this is the difference mu1 minus mu2, x minus mu and x minus mu whole transpose. This turns out to be a 2 by 2 matrix, right? So this is 2 into 1 and this is 1 into 2. So this falls to be 2 by 2 matrix. So 1 into 1 would be 1, 1 into 1.8 would be 1.8, minus 1.8 minus 1.8 whole square. Okay, so this is 2 by 2. So this will be a 2 by 2 matrix, 2 by 2, 2 by 2, 2 by 2, 2 by 2. Sum of all of them would be a 2 by 2 matrix. So that's how you calculated S1. Same way goes to S2. Just take every point in x2, 9 by 10 and its mean. 8 minus 4. this subtraction whole square, it's nothing but x minus mu 2 into x minus mu. Whole square is nothing but a representation of transpose. Okay, I just showed that example over here. So this becomes a 2 by 2 matrix. This becomes a 2 by 2 matrix. This becomes 2 by 2, 2 by 2, 2 by 2, 2 by 2. So everything would be 2 by 2. So now SW is sum of S1 plus S2. So sum this matrix with this matrix, you will get this one. So you got SW now. The second thing is you have to calculate SP. SP is nothing but mu1 minus mu2 into mu1 minus mu2 whole transpose. So now you know mu1. You calculated mu1 here and you calculated mu2 here. Subtract, subtract. So this becomes 2 by 1 into 1 by 2. This becomes 2 by 2 matrix. So SP is also a 2 by 2 matrix. Right? Now what you have to take the inverse of SW, multiply that with SP and calculate the eigenvectors of this. That will give you W, which is the direction which you are trying to find out. So to calculate the eigenvectors, the first thing you have to do is calculate the eigenvalues. To calculate the eigenvalues, what you will do? You will do the matrix A minus lambda I and then solve the lambda. Okay, so SW inverse, what we have got for SW is nothing but 3.3 minus 0.3 minus 0.3 into 5.5. Take the inverse of that, multiply that with SP. We got SP as this. So multiply both of them, minus lambda into I is this one. So and then after solving this equation, we got lambda 1 is equal to 0 and lambda 2 is equal to 0. So these are the eigenvalues. To maximize W, do we need to take the highest eigenvalue or lowest eigenvalue? What we have to do as the next step? Do we need to arrange the eigenvectors in descending order, or to get the highest value for W, do we need to take the lowest value of lambda? This is our equation, the SW inverse SP. W is equal to lambda W. We are trying to maximize this W. Find out the maximum value for W. The maximum function is J of W. So now, do you want lambda to be high or low for this J of W to be maximum? As J of W is maximization problem.
High value.
High value, right? So that is what we have done for PCA as well. PCA, we have arranged the eigenvectors in eigenvalues in descending order, and the first eigenvector corresponding to the highest eigenvalue would be the principal component one. So similar way, we calculated the eigenvectors for 0 and 1. So when eigenvector is 0, this is the eigenvector 1. I mean eigenvector, when eigenvalue is 12.207, this is the eigenvector. But for optimization, we have to take the highest eigenvector. So the eigenvector would be this one. So the optimal projection is the one that give maximum lambda, which is equal to J of W. So we have to take the largest eigenvalue. Now the equation becomes, what does this equation becomes? What are our dimensions given here? Dimensions are x1 and x2, right? So this becomes, this has to be multiplied with x1 and x2. So this becomes 0.9088 into x1 plus 0.4173 into x2 would be the LDA function. Okay, so this would actually separate both the points. Okay, understood? So this is how we derive the equation for LDA.
Yeah.
Okay, so that is the equation we have seen in the first screenshot. So I was telling you, right? So alpha x1, alpha x2. So we just have to find out alpha 1 and alpha 2. So that is found out here. Right? So that is actually found out here. Got it? So this is what LDA actually means is. Did you understood what LDA actually means? You got some understanding of it?
Yes.
Okay. Right. And then we need to talk about something called as I'll cover few things that are left over. One is singular. I mean, I told about three dimensionality reduction techniques. One is PCA, other one is LDA. What is the third one?
ST.
ST.
SVD.
Yeah, what does SVD stands for? Singular value decomposition. What does PCA stands for? What is the full form of PCA?
Principal component analysis.
What is LDA?
Linear linear discriminant analysis.
Linear discriminant analysis. So as I told you, I would like to compare. I would also like to explain you what is that singular value decomposition. But to understand singular value decomposition, you need to understand few concepts. That is what I'll drive through, and then at the end, the SVD is a simple calculation. It doesn't have any intuition other than I mean PCA that we have seen. Okay, just let's understand few mathematical concepts again, and then we can wind off for today. And I'll also share you the assignments that you have to solve. I think we have you solved two, I guess. Okay, so we have like three more for today. Two more assignments for today. But let's understand what is this matrix multiplication. We are doing lots of matrix multiplication so far, right? So now you have to actually understand what actually a matrix multiplication is. Okay. What does it saying? Like the transformation applied by a matrix is essentially a linear combination of the original vector components. Okay. Each row specifies how much weight to give to each component of the original vector when determining the new value in the transformed vector is what matrix transformation is. It looks a little complex, but I'll break down this, and I'll try to show you this. Okay. So let's take a simple example, and then you will actually understand this. I'm going to take a new matrix A 2 0 0 3. Okay, this is my matrix A, and I said matrix multiplication will actually do a linear transformation. It transforms the vector is what I'm saying. Okay, let me just take -3 for better understanding. Okay, right. So this is a 2 by 2 matrix. That means this is a point space in two-dimensional, and that is represented by R2. That is nothing but a two-dimensional space. So I am talking about a two-dimensional space here. Now I'll take one point which is 2, 4. This is my point, original point. This is 2, and this is something like 4. This is 4 and 2. Okay. Now let's look at what happens if I multiply this number with this matrix. 2 0 0 minus 3 into 2 and 4. Okay, just look at what is the new value. When you multiply this, what is coming up? 2 into 2 is 4. 0 into 4 is 0. So that becomes 4. 0 into 2 is 0. Minus 3 into 4 is minus 12. Okay. Now, if I draw this point again, what is that I'm getting? This 2, this 4 is giving us this vector, right? 2, 4. Now the transformed point is coming to be is looking like this. How is the transformed point looking like? It is 4 and minus 12. 4 and minus 12. Minus 12 would be something like this. Minus 12. And this is the resultant vector. This is the transformed point that we have got 4 comma minus 12. So when this vector is multiplied with this matrix, this is the new vector that we have got. Okay, understood? That is a new vector that we have got. Let's carefully observe few things. So this is the original point, and this is multiplied with this vector, and this is the resultant point, which is a transformed point. When multiplied with this is the resultant point that we have got. Okay, that's good. We understood something out of this, right? Now let's understand this intuitively. Okay, let's understand this intuitively. So now let's suppose linear combination of original vectors is what it is saying. Let's come back to this. Each row specifies what is the each row means. This is one row, this is second row, right? Each row specifies how much weight to give each component of the original vector. So this row specifies how much weight to be given to this vector, how much weight to be given to this vector in the transformation. So now it has given 2 times more importance, but no importance is given to the y vector. 0 means no importance is given to this y component, whereas the x component is multiplied twice. Okay, that is the reason you are seeing this 2 multiplied to be 4. Okay, even if you take another vector, if you take any other point, let's suppose if you take 3 comma 6, so you will get 6 comma, for now we are just talking about only x component, because there is no importance given to the y component. Okay, only importance is given, the first row specifies the weight to given to, I mean how much weight to give to each component. The first row specifies each row, or in specific you can say each row specifies how much weight has to be given to the each component of the original vector. This is our original vector, so it has not given any importance to the first row, has not given any importance to the second component when it is getting transformed, but it is multiplied by 2 times. The x component is multiplied by 2 times. That is the reason if you take any point like 3, 4, 5, 6, anything, that just gets multiplied by 2. That is how it is transforming this point to a new space. I mean it's rotating, it's just, see, it's just rotated this point to this direction. Now if you take the second row, it has not given any importance to the first component, which is x. It has minus, means it reversed the angle, it reversed the direction, and then it got multiplied by 2 times. So the positive y became negative, and the length of it became thrice of this. Okay, if it is 4, it became minus 12. If it is positive, it is coming to be negative. Okay, the second row has given that much importance to the second component of it. Understood? That is what matrix multiply, I mean that is what linear transformation is. Now if you take another example of just 2, 0 as matrix A and 2 comma 4 as the original point, what this says, there is only one row, there is no second component. Okay, so what this says is what is the length of it? This is 2 into 2, this is 2 into 2, and this is 2 into 1, so we get 1 into 1. So it is transforming a vector to a point. Okay, it is converting a 2-dimensional point to 1-dimensional point. That means what it is doing, 2 into 2 is 0, 0 into 4, 0. So it became 2 into 2, which is 4. That means a 2-dimensional data point is converted to a 1-dimensional point, and it is multiplying that x component to twice. So look at this, that this is a dimensionality reduction, right? So now the original point is 2 comma 4, which is in 2 dimensions. Now once this is multiplied with this matrix, what it is doing, it is converting down this point to a 1-dimensional point. So that new 1-dimensional point is a point on x-axis. It is converting a 2-dimensional point to 1-dimensional point. Okay. Similarly, you can take a three-dimensional point and understand this. So the y component here is 0. There is no z component. The only component that is there is x component. So it is converting two-dimensional data points to one-dimensional data points. Okay. That is what actually it is. That is a into the vector that you are transforming. So this vector is getting transformed from two-dimensional to one-dimensional, or in the same dimensional spaces it is rotating or scaling or something of that sort is happening. That is what that is why we are saying matrix multiplication is a linear transformation. So there is another example that I can give you on three-dimensional, which you can actually map with your learnings in principal component analysis. So let's take another example, and with this I think we will be clarified. Let's take a three-dimensional point, and I would say the three-dimensional point is 1 2 3. Okay, this is a three-dimensional point. Now I got the matrix A as 1 0 0 0 1 0. Okay, so this is 2 into 3 matrix. So this is 3 into 1 matrix. Okay, 3 into 1. So this is a three-dimensional point. This is a three-dimensional point, and this three-dimensional point is getting transformed to two-dimensional point. When you're multiplying this with this, it is converting to a two-dimensional point. Just look at this. So x is coming to be only x. If you take the first row, it is giving 0 weight to the other components, 1 weight to the initial component. So this becomes 1, and this is 0 1 0. That means like it's not giving any importance to x, it's not giving any importance to y, it is giving importance only to the x-axis. So now there is no z component. So there is no component, there is no row which has given any weight to the z component, right? So that is the reason it is coming down to be 1 2. So what is this looks like? So if I better represent this point, so on this plane, this is, let's suppose this is x, y is 2, and z is somewhere like 3. So the point is on x this way, it comes down to it goes up, right? So something like this is z axis, so it goes up, and that is 3. This is 1 2 3. This is a point floating in the room. Okay, now you're converting the three-dimensional point to two-dimensional point, because I mean, you're multiplying that with a matrix of 2 into 3. So it is transforming three-dimensional spaces to two-dimensional space. So now the new point would be 1 comma 2, which is the projection of the point onto x-axis. So that is how you're transforming the point from one dimensionality to the other dimensionality. Okay. So that is what actually it is. So when you are seeing this, when you're taking only one eigenvector, so eigenvectors are basically d by d matrix, right? Number of dimensions into number of dimensions, right? But if you're reducing the number of dimensionalities, I mean number of columns based on the variance, you're transforming the points from higher dimensionalities to lower dimensionalities. Okay, that is what actually it is. Understood? A vector in 3D points in 3 dimension is transformed to a vector in 2-dimensional points when it is multiplied with a component. Let's suppose if you have something like this 0 1 0 in one of the dimensions, it is actually giving importance to y again, so that becomes the third dimension. Okay, so when you completely avoid the third part of it, you are just transforming from one space to another space. I mean, 3 dimensionalities to 2 dimensionalities. Any point that is getting multiplied by from this is getting transformed from 3 dimensionality to 2 dimensionality. Did you understand what is this matrix multiplication and how it is transforming the points from or how it is actually scaling or rotating or transforming from one dimensionality to other dimensionality? We have seen examples of a point getting scaled, getting rotated from positive axis to negative axis, and we also have seen one of the components is getting reduced. I mean, a 3D point is transformed to a 2D point when multiplied with a matrix. So these are all the matrix multiplications. So the matrix multiplication is actually transforming the points, rotating the points, scaling the points, and also reducing the points from higher dimensionality to or projecting the point from higher dimensionality to the lower dimensionality. So that is what actually the matrix multiplication is doing. Okay, right. Uh, so look at everything. You can look at matrix as a vector also, right? So this is one of the vector. This is one of the vector. This is one of the vector. Just multiplying those vectors with something else. Right. This is how you have to understand when I say matrix multiplication will do a linear transformation. Transformation would be nothing but it's an as I said, transformation can be scaling, rotating, or dimensionality reduction, or projecting the point from higher dimensions to lower dimensions. That is how we are getting linear transformations when we are actually doing you know matrix multiplication. And eigenvalue decomposition, this is an important concept which I haven't completely covered in the last session. In the last session I have spoke about this in the last minute, I think, which would not be clear, and I won't expect that to be clear for you, but today it would be clear. What is the actual purpose of eigenvalue decomposition is what you're trying to understand. Okay, when I say eigenvalue decomposition, you know A of lambda is equal to u of lambda, or lambda into u. I'm sorry, A into u is lambda into u, where lambda is the eigen value and u is the eigenvector. Okay, so the eigenvalue representation or of this is the A into u is equal to lambda into u. So u is the eigenvector of A and lambda is the eigenvalue of A. So we want to do an eigenvalue decomposition. How you can do that is if I multiply with u inverse on both the sides. Okay, let me say I am going to multiply. I mean, this in matrix notation, this can be represented like this, right? So this would be u1, and this would be u2 vector. Okay, this is u1 vector. U1 can have x component, y component like this, right? u1x, u1y. u2 component would be u2x, u2y. So the u vector would be u1x, u1y in matrix notation, u2x, u2y. So I'm representing this whole thing as this one. Okay, I'm representing this whole thing as this one. That becomes lambda into u1, u2. Okay, I'm multiplying with the inverse of this matrix. Okay, I'm multiplying on both sides with u inverse. So that becomes u into u inverse will become I. So this becomes A is equal to u inverse of lambda into u. Okay, so u inverse into lambda of u. What is lambda here? Lambda is nothing but the eigenvalues along the diagonal elements. Okay, so that is what lambda basically is. It's an the eigenvalues will be the diagonal elements of this lambda matrix. If I represent the lambda in matrix form. So what this finally falls out to be is uh, what should I tell you? So that is what, if I multiply with u inverse on both the sides, A become u inverse lambda into u. Okay, so till this point you are clear, right? So just multiplying u on both sides, and u inverse lambda u is the representation for A. Okay, now
Yeah.
now let's understand why this is why this decomposition is important. It's just decrease the computational efficiency, and I'll let you know how it actually decreases the computational efficiency. Mhm. Sounds good. Okay. So now, let's say this. This is the eigenvalue decomposition of A is what I'm saying, right? Why is this useful is, do you understand why, how does it is turning to be this matrix, how lambda is turning to be the eigenvalues along the diagonal elements? The reason is just simple. If you take, what is this? If u1 is the eigenvalue, eigenvector 1 of A, right? So this can be lambda 1 u1. This can be represented like this. A into u2 is equal to lambda 2 into u2. Okay. So you know lambda 1 is equal, let's suppose this, if you take this example, how does it looks like? So u1 u2, this is 1 into 2, and this is lambda 1 0 0 lambda 2. Okay, just multiply this. What is this coming to be? u1 lambda 1 and ut into 0 will be 0, and this is 1 into 2, and this is 2 into 2, so this becomes 1 into 2. And the next thing is u1 into 0 is equal to 0, u2 into lambda 2. So is this matching the right sides? And on the left side, a into u1 is a u1, a into u2 is a u2. Okay, so a u1 is equal to u1 lambda 1, a u2 is equal to u2 lambda 2. That is why eigen lambdas has to be the diagonal elements. Once the eigenvalues are the diagonal elements of this matrix, you will get this these notations when even when you do the matrix multiplication. So that is why I'm representing lambda as the lambda is nothing but the eigenvalues along the diagonal elements. Okay, you understood that? Understood?
Yeah.
Okay, so this is the eigenvalue decomposition of a particular matrix. But why this is important? How it actually helps us in real world is something that you have to understand. This is the representation that you have already understood. So now let's understand what is the importance of this. So let's suppose if you are trying to calculate a to the power of p. Okay, you are trying to calculate a to the power of p. This is what you're trying to find out. So when you're trying to find out a to the power of t, what you have to do, a into a into a into so on a to the power of p. So you have to multiply these two matrices to get a square, and then you have to multiply these two to get a square, so on. And then again you have to multiply this two to get a to the power of 4 and a to the power of 4. So you keep on doing these to get the a to the power of p. So that is how you have to multiply the matrix a to the power of p, right? So this actually requires, do you know that algorithm? What is that sorting algorithm where we have, what is that algorithm? That is called as insertion sort, which has divide and conquer algorithms. Do you remember how that actually works? Insertion sort.
Yeah.
Have you ever heard about insertion sorts?
Insertion beginning random location.
Is that insertion sort? I don't know which I put. No, insertion sort is not the one. What is that sorting algorithm? Insertion.
Shooting.
What is that? Quick sort, I guess. Quick sort, and we
Okay.
also use the other sorting algorithm. What is that? Yeah, quick sort is one of the things. So look at this. It is actually dividing the matrices. So if this is the matrix that is, I mean, if it is the array that is given, it is breaking that into two parts, and then it is subdividing that. I mean, it is further breaking that, and at the end, it is actually sorting all the values into this. So this is called as divide and conquer algorithms. So such kind of we have another sorting algorithm like quicksort only, which is also divide and conquer algorithm. So the if you look at the
Bubble
computational,
sort.
it's log of and to how much time it would take. It is no, bubble sort is also not. Bubble sort is a normal algorithm, which is order of n square. Um, it has worst time complexity order of n square. Quicksort is order of n square. It's sorting as n log n complexity.
I guess merge.
Merge sort. So if you go see the merge sort, so it is actually dividing the matrix, and then it is actually sorting them and then bringing them back again. So order of this is n log n. Okay. So we are just where we are doing, we are just breaking down. We are not combining them back. So the number of times that we have to do this operation is order of n. Okay. Order of log n times we have to do these multiplications. Okay. Let me go back to the PPT. So when you are doing I mean, for calculating a to the power of p, the number of calculations that it takes is log to the power of log of p. Okay. So it's taking log of p calculations, log of p times of calculations. So, but when you convert this to, when you use this eigenvalue decomposition, the same a to the power of the same a to the power of p can be calculated this way. So a to the power of p is nothing but a into a into a into a, right? So I am replacing a with u to the power of minus 1 lambda u into u to the power of minus 1 lambda u into u to the power of minus 1 lambda u, so on, right? So just look at this. U dot u inverse is nothing but I, right? U dot u inverse is nothing but I. So this turns out to be u to the power of minus 1 lambda to the power of p into u, right? Lambda is a diagonal element, diagonal matrix. So this is lambda 1 0 0 lambda 2. So to the power of p is nothing but lambda 1 to the power of p 0 0 lambda to the power lambda 2 to the power of p, as this is a diagonal element matrix. So now number of calculations that we need is just two calculations here. I mean, this is one calculation and the whole thing will be two calculations. So a to the power of p, when you use eigenvalue decomposition, it is getting completed in two calculations, whereas it takes log to the power of p calculations. As p is increasing, let's suppose p is 10,000, how many number of calculations that we need? Log to the power of p means how many calculations that we need? This is log to the base e. So that becomes, what is log 10,000?
Four.
Log 10,000 to the base e is 4.
Yeah. 4 answer.
Okay, anything. So as p is going to be high value, this is going to increase, right? Whereas this would remain very constant. Okay, so this, we can just minimize the complexity of calculations. It can be just done in with just two multiplications. This is one of the applications of using eigenvalue decompositions. Okay. So this is one of the advantages, and this is what eigenvalue decomposition is. And this is why the eigenvalue decomposition will be really useful in computational perspective. The calculation of a to the power of p is just an example. And you have to understand what is inner product and outer product. Okay, what is matrix inner product and what is matrix outer product. So let's just take an example of x into x transpose into x. Okay, let's take x as something like this one: $10, $100, $200. Okay, instead of x into x transpose, let me take this as x into y transpose, x transpose into y. X into y transpose, x transpose into y. Okay, what does this actually gives you? Something what you have to understand. Okay, so let's take y as something like 0.1, 0. What's the best value to do? This is also 0. You can take anything technically, 0.05 or 0.02. Okay, so this is y. Now the first question for you is x into y transpose, x transpose into y. What would be the dimensionality of this product and what would be the dimensionality of this product? What is the dimension that you'll get here? X is 3 into 1, right? X is 3 into 1. Y transpose is 1 into 3. So the product of this would be 3 by 3 matrix. Okay. What is the product of this? It would be x transpose would be 1 into 3 and y would be 3 into
1 into 1.
1. So you're getting 1 into 1. So x transpose into y is giving you a scalar value and x into y transpose is giving you a matrix, right? Right or not? X into y
Yeah.
transpose is giving you a matrix. Now, let's just understand this conceptually. Let's suppose these are the dollars that I have spent, okay, on my trip. 10 would be the amount that I have spent on my meal, 100 would be on travel, $200 would be on my hotel. I spent $10 on my food, $100 on travel, $200 on my travel. So this is the tax. This is the city tax, state tax, and federal tax or central tax. So these are the different taxes on each amount that I have spent. Now, what does x comma y transpose will give you is, it gives you the breakup of each tax on the money spent. So it will give you 10 into 0.1. That means the tax that is incurred by city on my $10 on my food, the amount of this is city tax, state tax, federal tax. This is again my spendings on food, travel, hotel. So this x into y transpose will give the breakup of every component to every other component. Okay, 10 into 0.05, 10 into 0.02. Okay, so it is giving the breakup of every tax component that we are getting. So out of $100, how much tax is incurred by city, how much tax incurred by, so this becomes 0.1, this becomes 0.05, 100 into 0.02. Okay, similarly 200 into 0.1, 200 into 0.05, The next one is, so this becomes 100, right? Sorry, this is all 200. On 200, what is the breakup order? Different taxes is what that will 200 into 0.02. Okay. So that this is giving the breakup of each tax on different components. So what does the other way of looking at it? What is the other thing that is what is this product is giving us? What is this product is giving us? Can anyone guess what does X transpose into Y will give you? Let me just do that calculation.
Single value,
What is that single value will represent?
scalar.
Yeah, that is scalar, but this is how it actually works, right? So this will not give you the breakup. What is the total tax that is been taken by the, I mean, let's suppose this is how you have to look like. So this is the spend of my amount on food. This is the spend that I have done on my travel, and this is what I have done on my accommodation. And now this is the total tax collected on my food. This is the tax collected on my travel. This is the tax that is collected on my, what is that? On my food. So what is the total tax that I have paid? That is equal to 10 into 0.1 plus 100 into 0.05 and plus 200 into 0.02. So that gives you a scalar value. This has the breakup and this has the total amount of tax that I have paid. Okay. So if you calculate this, what is that? It is giving it to you. It is giving to you a scalar value, which is the total amount of tax that you have paid. Okay. So this is like multiple components has multiple breakups. Okay. I mean, the single component has multiple breakups. Here, single component has a single component. So that is the reason you're getting a scalar value. When a single component has different breakups, you will get a matrix of 3 by 3 into matrix. So we call this as an outer product. We call this as an inner product. Inner product is always a scalar value and it will not have any breakdowns. I mean breakups, whereas an outer product will have a breakups. I mean one component in X will have different components in Y, whereas one component in X will have a single component in Y. That is the difference between inner product and outer product of a matrix. So many times we have seen X transpose into Y into XY whole transpose, right? That is what actually it means is. Okay, so that is what about inner product and outer product. We have seen about eigenvalue decomposition and what is the advantage of eigenvalue decomposition, and we also have seen how the matrix multiplication is actually transforming the points on one space to the other space, scaling and all that stuff, right? That is all what we have learned so far, right? I think what else we plan to cover today? I think that's all we have for today. One last thing is that's okay. So I think that's all for today, and let's spend some time on where we are. Stop the recording first.